In the late 1800s, one vessel threatened to change naval warfare forever. The Peral was the first modern military submarine and the first fully electric one, able to fire torpedoes and navigate underwater for hours when many ships still sailed the oceans under wind power. It was meant to be the crown jewel of the Spanish Armada. A U.S. admiral even admitted later that just one could have changed naval warfare in a single day. But before it ever saw battle, it vanished. To understand just how mind-blowing this engineering feat was, we spent hours rebuilding the entire Peral submarine in 3D to show how it worked and why it never made its mark on the battlefield. Submersible vessels had been imagined and occasionally attempted for centuries. But most early designs were crude, human-powered craft that achieved only limited success beneath the water. By the late 19th century, however, several new technologies were beginning to change what seemed possible. Lead-acid batteries, electric motors, and self-propelled torpedoes were all emerging at the same time, creating the ingredients for a truly practical submarine. Spanish naval officer and engineer Isaac Peral recognized the potential. He realized that these technologies could be combined into a single radically new type of warship. The project soon gained new urgency after the Caroline Crisis of 1885, a dispute between the German Empire and the Kingdom of Spain over control of the Caroline Islands in the Western Pacific. During the incident, a German gunboat entered Spanish-owned islands, raised the German flag, and asserted Germany's claim, an act that starkly exposed Spain's vulnerability across its overseas possessions. The incident pushed the Spanish government to support Peral's proposal to develop a submarine. Initial work began in September 1885, and just 3 years later, the vessel was launched. During sea trials, the Peral submarine proved it could do what many believed impossible: navigate underwater, maintain a controlled depth, and launch torpedoes. And that is only the beginning of what this remarkable machine was capable of. The Peral submarine was built as a single-hull vessel constructed from riveted steel plates. In a single-hull submarine, only one layer of steel separates the crew from the surrounding ocean, a thin barrier between the sailors inside and the pressure of the sea outside. Despite its compact size, the vessel packed remarkable capability. It weighed around 77 metric tons, measured 22 meters in length, which is about the length of 2 city buses, and had a beam of just 2.9 meters. On the surface, it could reach 7.8 knots. Underwater, it could travel at about 3 knots. It could dive to a maximum depth of around 30 meters. These capabilities were made possible by a set of unusual systems, some of which were so advanced their exact workings were kept secret. Inside this narrow steel cylinder, a crew of up to 11 sailors operated the entire submarine. In a confined space like this, every crew member had a critical role. If someone became sick during a mission, hundreds of miles out at sea, there wasn't a doctor available. Thankfully, most of us aren't out at sea. But even on land, finding the right doctor can still feel harder than it should, especially when you don't know where to start. And if we're being honest, most people put it off. Not because they don't care, but because the process is a hassle. The searching, the calls, the waiting. That's exactly why tools like ZocDoc, today's video sponsor, exist. ZocDoc is a free website where you can find and book doctors all in one place. You can search by condition, read verified reviews, and see real-time availability. With over 150,000 providers and 200-plus specialties, it makes it easy to find care that fits your needs, whether it's in person or a quick video visit. What makes it useful is how simple it is to actually take action. You can find doctors who listen and care, check their schedules, and book instantly, often the same day or within 24 to 72 hours, without calling or going back and forth. If something's been on your mind, this is a simple way to finally take that step. Head to ZocDoc.com/deconstructed to find a doctor that's right for you. Now, let's take a closer look at the submarine itself. At the stern or rear of the vessel were the main propellers. 2 propeller shafts each drove a 3-bladed propeller, rotating in opposite directions to generate forward thrust. Just ahead of them were the diving planes, mounted on either side of the aft section between the propeller shafts and the hull. These control surfaces adjusted the submarine's pitch during dives and ascents. Steering was handled by a set of rudder blades positioned above and below the hull. By turning these rudders port or starboard, the crew could change the submarine's heading. A protective framework surrounded the rudder assembly, shielding it from collisions and supporting the shaft that controlled its movement. Beneath the hull were another unusual set of devices known as depth propellers. Mounted at both the bow and stern, these propellers helped submerge the submarine and maintain stability while underwater. They were operated by one of Isaac Peral's most closely guarded inventions, a highly secretive depth control device that allowed the vessel to regulate its position beneath the surface with remarkable precision. We'll take a closer look at how that system worked a little later. Moving forward toward the middle of the submarine, 2 ventilation cowls were mounted along the top of the hull, both forward and aft. These provided fresh air while the submarine operated on the surface. At the center of the vessel rose the central turret, a small raised structure above the hull. It contained several portholes and observation windows, along with the main hatch used by the crew to enter and exit the submarine. Mounted on top of the turret was a dome-shaped housing that contained the submarine's compass, used for navigation. Forward of it was the periscope, a fixed observation tube that allowed the crew to watch the surface while the submarine remained submerged. But this was not the kind of periscope most people imagine today. Its design was far more unusual, and we'll reveal exactly how it worked later in the video. On either side of the turret were small platforms with handrails, used by the crew when boarding the vessel or during operations on the surface. Along the upper portion of the hull were also several small portholes, which allowed natural light to enter the submarine's interior. Finally, at the very front of the vessel, the bow, was the outer door of the torpedo tube. From the outside, it appeared as a circular cap at the extreme end of the hull. This tube allowed the submarine to launch torpedoes toward enemy ships. The outer door was opened and closed using a worm drive mechanism. Inside the hull, a crew member turned a hand crank connected to a shaft. At the outer end of that shaft sat a worm gear, which meshed with a worm wheel attached to the hinge of the external torpedo door. As the crank turned, the gears slowly rotated the door open or shut. The Peral submarine was one of the most advanced naval machines of its time, and yet it would disappear before it ever entered service. That's why we turned this entire reconstruction into a poster of the submarine, mapping out its every detail. Grab yours through the link in the description. Every purchase directly supports the channel and the team behind it. We're also giving one away. For a chance to win one, like this video, subscribe, and comment below. What surprised you most about the Peral submarine? We'll announce the winner in the next video. And a quick shout out to our last giveaway winner. Congratulations! Now, let's open the hatch and step inside the Peral submarine to uncover the unusual systems that allowed it to operate in ways no other vessel of its time could. At the stern of the submarine were the systems responsible for propulsion with several key components. Propulsion was provided by 2 22-kilowatt electric motors, each driving its own propeller shaft. The motors were connected to the shafts through a reduction gear system. A small pinion driven by each motor turned a larger gear coupled to the propeller shaft, creating a 3-to-1 reduction ratio that allowed the motors to spin efficiently while delivering the necessary torque to the propellers. Between the 2 propulsion shafts sat another motor. This 3-kilowatt electric motor powered the aft depth propeller, transmitting motion through a bevel gear arrangement. An identical unit was installed at the bow to drive the forward depth propeller. Directly forward of the aft depth propeller motor was the ballast tank water pump. This pump filled ballast tanks located along the bottom of the hull, allowing the submarine to adjust its buoyancy before descending using the depth propellers. Forward of the pump, positioned between the two propulsion motors, was a piston air compressor. Its job was to compress air into storage tanks mounted inside the hull at midships and at the bow. This compressed air served several purposes, most notably launching torpedoes and helping regenerate breathable air inside the submarine. Mounted above the compressor was a 4-kilowatt electric motor that could power either the compressor or the ballast pump. A selection lever located beneath the motor operated a bevel gear selector mechanism, allowing the crew to engage whichever machine was needed at the time. Just forward of the propulsion motors was the diving plane control wheel, used by the crew to adjust the submarine's diving planes and control its pitch during ascents and descents. Moving forward into the center of the vessel, we reach the section dominated by the submarine's batteries. These batteries occupied more interior space than any other component on board. In total, the submarine carried 613 battery cells, which supplied electrical power to the entire vessel. Altogether, they weighed approximately 30 metric tons. If the submarine was operating on the surface at 3 knots, this battery system provided a range of up to 400 nautical miles. Directly beneath the central turret was the command center. Just below the entry hatch sat a second control wheel used to operate the rudder blades. The turret's windows allowed the crew to see directly outside while navigating on the surface, a particularly useful feature during docking maneuvers. Also located in the command center was the optical table, positioned beneath the periscope tube. At the top of the periscope tube was a prismatic lantern. Inside it, a reflective element redirected the outside view down the tube and projected the image onto the optical table whenever the lantern was raised above the water's surface. The table itself could be raised or lowered to bring the projected image into focus. By observing that image, the crew could estimate the distance to a target and calculate firing solutions for their torpedoes. Aft of the command center was one of the most intriguing components in the entire submarine, Peral's depth control device. It was considered to be one of Peral's most important innovations. Yet its exact operation is not well documented, partly because Peral himself was extremely secretive about the design. Based on surviving drawings, however, it likely worked in the following way. The device appears to have been based on a pendulum and hydrostat control system, similar to the mechanism used in early torpedoes to maintain a constant depth automatically. The system was mounted on a base plate supporting 3 main components. The first was the hydrostat, a mechanism used to sense water pressure. Peral's hydrostat consisted of a Borden tube, a long flattened tube bent in a sinusoidal shape. One end of the tube was fixed to a frame and connected to the sea outside the hull through a pipe. As the submarine dived and external water pressure increased, the tube would gradually stretch, pushing its free end outward along tracks on the frame, guided by small wheels. But if the submarine relied on the hydrostat alone, it would tend to oscillate around the target depth rather than hold it steady. To address this, the system also incorporated a pendulum suspended from the top of a separate frame. The pendulum detected the submarine's pitch, sensing whether the bow or stern was angled upward or downward. The third component was an electrical contact plate, which likely acted as a switch. Pivoting around a central axis, it could activate the forward depth propeller, the aft depth propeller, or both, depending on its position. The 2 control inputs, depth and pitch, were then combined through a mechanical linkage that regulated the submarine's depth. The moving end of the Borden tube was connected to a rod that drove the upper end of this linkage, while the lower end, the controller's output, operated the contact plate through another rod. The position of the linkage determined how strongly each input influenced the system. In effect, the device functioned as an early form of proportional derivative control, a concept that remains fundamental in many industrial control systems today. Finally, the system included a bell and a horn, which likely served as warning indicators whenever the submarine experienced extreme pitch angles or significant depth deviations. Moving toward the bow of the vessel, we reach the torpedo launch system. The submarine's torpedo tube was fitted with 2 watertight doors, one at each end. This design allowed the submarine to launch a torpedo while fully submerged. The vessel carried 3 torpedoes in total, one loaded inside the tube, and 2 additional torpedoes stored inside the submarine as reloads. These were Schwarzkopf torpedoes, German anti-surface ship weapons used in the late 19th century. They were constructed from bronze, which helped resist corrosion in seawater. Each torpedo weighed 280 kilograms and measured 4.5 meters in length. The torpedoes were powered by compressed air stored in a tank inside the torpedo itself. This compressed air drove an engine that turned 2 counter-rotating propellers. The air tank could be recharged in about 8 minutes using the submarine's onboard compressed air supply. Launching a torpedo followed a specific sequence. With the torpedo already inside, the tube was first flooded with seawater. The crew then rotated the hand crank to open the outer tube door. A burst of compressed air from tanks mounted above the tube pushed the torpedo outward. Once clear of the tube, the torpedo's own compressed air engine started, spinning its propellers and sending it toward its target. Their effective range reached up to 400 meters, with a maximum speed of 25 knots. Each torpedo carried an explosive charge made of gun cotton, an early high explosive that was detonated when the weapon struck its target. To show exactly how the tube was reloaded after firing, and how the torpedoes were loaded inside the submarine, we also made a dedicated deep dive video that breaks the sequence down in detail, available exclusively to our YouTube and Patreon members. And finally, like any vessel intended to operate for extended periods, the submarine also included a toilet. This one was particularly advanced for its time, engineered to use compressed air to expel waste directly into the sea, even when the submarine was fully submerged. Despite performing successfully during its trials, the Peral submarine never entered active military service. The project was ultimately abandoned, undone by political opposition and a deep skepticism towards submarines within the Spanish Navy. In 1890, the vessel was withdrawn from service. Its equipment was removed, and the submarine itself was placed into storage. Years later, demolition was even ordered, but the order was never carried out. Just 8 years after the project was abandoned, Spain went to war with the United States. During that conflict, the Spanish fleet was decisively destroyed. Looking back, U.S. Admiral George Dewey reportedly reflected on what might have been when he said, "If Spain had used even one submarine like those invented by Peral, I would not have been able to sustain the blockade for even 24 hours." Today, the hull of the Peral submarine survives and can be seen at the Cartagena Naval Museum in Spain, preserved as a rare artifact from one of the most forward-thinking naval experiments of the 19th century. The submarine stands as one of the great what-if moments in naval history, a design that appeared decades ahead of its time, but arrived before the world was ready to use it. More than a century later, Isaac Peral's legacy continues. In 2023, the first attack submarine of a new class, named Isaac Peral, entered service with the Spanish Navy. While some underwater vessels were built for war, others were built for exploration. In 1960, less than 70 years after the Peral submarine, the bathyscaphe Trieste carried humans to the deepest place on Earth. We broke down how it was built and how it made that historic dive in this video, so be sure to check it out. Thanks for watching. Stay curious.